Hi, welcome to today's session on math as a second language. And this is one of my favorite topics in terms of the adjective-noun theme again, to show how multiplication, if we use the adjective-noun theme, is just a very efficient way to compute large multiples of a particular number. Now, again, just to refresh your memory, but what we mean by the multiples of 9 are the numbers that we get if we count by nines. Like the third multiple of 9 would be 3 times 9, or 27. 4 times 9 would be called the fourth multiple of 9, etc. So let me start with a little anecdote that I think your students might find interesting. It does look a bit like a magic trick when you first start out, but it's the story of the young boy who was very, very conscientious, did all of his homework usually, but sometimes got very careless. And when he got careless, he got upset with himself. And one day, the teacher told him, tomorrow they're going to have a test on knowing the multiplication table for 9. And the boy went home, and he got all flustered and forgot to do his homework. He came in the next day, what he saw on his desk was this problem. Now, he knew that 1 times 9 was 9, but he hadn't studied, and he didn't have a hint as to what the others would be. But he figured because he was negligent, the least he could do was save his teacher some work, and that he would correct the paper for her. So he said, I have 1 wrong, 2 wrong, 3 wrong, 4 wrong, 5 wrong, 6 wrong, 7 wrong, 8 wrong. He said, but the way my luck is running today, I probably even counted wrong, so I better double check. So he started at the bottom and counted 1 wrong, 2 wrong, 3 wrong, 4 wrong, 5 wrong, 6 wrong, 7 wrong, 8 wrong, and was petrified of what his final grade would look like, and was completely startled when he found out all the answers were right. Now, the reason they were right, I think this is an interesting anecdote in its own right, is that look what happened here. Every time you increase this column by 1, you are adding on 10. And every time you decrease this column by 1, you are subtracting 1. Well, if you add 10 and subtract 1, that's the equivalent of adding 9. And by the way, that keeps the sum of the digits the same, something we may not have realized. If you add up all the sums of the digits here, 1 plus 8, 2 plus 7, 3 plus 6, 4 plus 9, 5 plus 4, they all add up to 9. And the reason is we added 1 to the tens place and subtracted 1 from the ones place, so the net difference from one line to the next is 9. Now, we could do this with any number. For example, when I went to school, we learned the multiplication tables through 12. Other places, nowadays, they do it through 9. But no one that I know of learns the multiplication tables through 13. So let's do the 13s table together. Now, what's a fast way of adding 13? You go to the store and you buy something for $13. Isn't it likely that you'd give the clerk a $10 bill and 3 ones? Well, I guess maybe a credit card, but we're doing this in terms of money. You probably wouldn't count out 13 ones. So a quick way to add 13 is to add 10 and 3 ones. Let's try it with the 13 table. 13 and 10 is 23, and 3 is 13 and 10 is 23, and 3 is 26. 26 and 10 is 36, and 3 is 39. 39 and 10 is 49, and 3 is 52. And we can keep on going this way, get through as many as to the 9. 9 times 13 is 117. This is quite a cute way of getting the table. Most students won't believe that this works. So there's a very good chance that when I show them that 6 times 13 is 78, doing it this way, they're going to check it more traditionally to make sure it was the same answer, and that way they're getting practice in multiplication. Anyway, let's suppose we're going on this way, and I want to find out what the 234th multiple of 13 is. In other words, what's 234 times 13? Well, I could keep on going like this for 234 lines. Very, very tedious, very, very big chance I'll make a careless error. But even if I don't make a mistake, this is still a very, very tedious computation to do. To make this sound a little bit more realistic, let's suppose I'm a salesperson, I'm selling pens, and I'm selling the pens at $13 each, and I sold 234 pens, and I want to know how much money I made. In other words, I made $13 234 times. Let me just repeat the table here for reference. And now let me show you where the adjective noun theme comes in. When we said that 2 times 13 was 26, we were talking about just the adjectives. What the 26 modifies depends on what the 2 and the 13 modify. In other words, 2 times 13 as adjectives is always 26. But what that 26 represents depends on what the 2 and the 13 represent. For example, 2 times 13 apples would be 26 apples. 2 times 13 hundreds would be 26 hundreds. By the way, notice that 2 times 1300 is the same as 2 times 13 times 100. And so I can regroup this by the associative and commutative properties to read this as 213s. 200 times 13 is 2,600. See, let's go through that slowly. 2 times 1,300 is 2,600. So 200 times 13 is 2,600. That means 213s is 2,600s. So 200 times 13 is 2,600. And notice right away what that tells me. I'm going to get to 213s before I get to 234 13s. And if 200 13s is already 2,600, I already know that whatever this answer is, it has to be bigger than 2,600. Already a big head start. Well, let's see how I can handle this. To add up 234 13s, just dealing with the adjectives here, is the same as adding up 13 234s. That would be what? 13 times 200 plus 3 10s plus 4 1s. And writing this without the words, remember math doesn't use words, it just uses numbers. It would be 13 times 200 plus 30 plus 4. Now, to make this more plausible in terms of being able to visualize this in your mind, let's suppose that the salesperson sold 200 the first day, 30 the second day, and 4 the third day. We can find out what the total amount was just by adding up the amount he made every day. So if you made 200, if 13 times 200 is 2,600, we know that on the first day he made $2,600. On the second day, 13 times 3 we already know was 39. So 13 times 3 tens is 39 tens or 390. So on the second day he made $390. On the third day he made 13 times 4, which from the table gives me 52. So he made $52 that day. Altogether he made 2,600 plus 390 plus 52, which is 3,042. And because we're dealing with dollars. Now this may be a little bit tedious, but wasn't this a lot faster than having to add up 234 separate 13s? Well, what happens is we present this in a shortcut notation where the student never gets a chance to really digest this. In fact, let's look at this in a little bit more detail. We showed that the answer was $2,600 plus $390 plus $52, and that came out to $3,042. Now, how did we check that? We checked that by multiplying 234 times 13 to see if that would give us 3,042. 3 times 4 is 12, put down the 2 and carry the 1. 3 times 3 is 9 and 1 is 10. Put down the 0 and carry the 1. 3 times 2 is 6 and 1 is 7. 234, blah, 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 and we get down to 3,042 this way. Now, what's interesting is these two numbers that we added don't look anything at all like these three numbers that we added. And the reason is that even though 234 times 13 is numerically equal to 13 times 234, in other words, as adjectives they're the same, there's a big difference between selling 234 items at $13 each and selling 13 items at $234 each. What we did in this problem was found the answer to how much money would we make if the items had cost $234 and all we did was sell 13 of them. The proper way to check it is that the adjective should be on the bottom. Now that may look strange to you because you were probably taught that the number with the more digits has to go on top. And the reason for that is The same reason we talked about last time. By putting the smaller number of digits on the bottom, you use up less rows, and that saves paper. It also obscures what really happened. Let's just do this, the same recipe, using the bottom number as 234 and the top number is 13. Nothing is going to change. 4 times 3 is 12, put down the 2 and carry the 1. 4 times 1 is 4 and 1 is 5. 3 times 3 is 9. 3 times 1 is 3. 2 times 3 is 6. 2 times 1 is 2. Notice what we do. Each row begins under the digit that we're multiplying by. We add these numbers up. Used up a little bit more space, but did we get the same answer? Yes. And notice that 0 is used as a placeholder. I don't have to put the zeros in here, because by putting the 9 over here, it was already in the tens place. But if I put the zeros in, notice immediately the connection between the 3 numbers I got this way and the 3 numbers I got this way. In other words, this way shows you how you very quickly added up 234 13s. Okay? And to use the adjective noun theme another way, let me show you what was really happening when I said 4 times 3 is 12, put down the 2 and carry the 1. When we multiply, did you notice that every digit on the bottom multiplies every digit on the top? But those are just the adjectives. The nouns are what column they're in. So when we said that 4 times 3 is 12, the 3 and the 4 were both in the ones column, right? So that meant, what? 1 times 1 is 1. So 12 in the ones column, that's the same as 2 ones and a 10. Then when we said that 4 times 1 was 4, what were the nouns? Ones and tens. And 1 times 10 is 10, so the 4 had to go into the tens place. Let's just complete the chart this way. 3 times 3 is 9. What are the nouns here? Tens and ones, that's 10, so the 9 goes into the tens column. Then we multiplied the 3 times the 1, that was 3, but what were the nouns here? 10 and 10. 3 tens times 1 10. 10 times 10 is 10 tens are 100, so the 3 goes into the hundreds column. And I can put these zeros in just for emphasis here. Then we multiplied the 2 times the 3. That gave us 6. But 6 what? The 2 was in the hundreds place, right? The 3 was in the ones place. 100 times 1 is 100, so the 6 goes into the hundreds place. And what did we do finally? The 2 multiplied the 1. 2 times 1 is 2, but what are the nouns here? Hundreds and tens. 100 times 10 is 1,000, so 2 goes into the thousands place. And what we wind up with is what? 12 plus 40 plus 90 plus 300 plus 600 plus 2,000. And I'll leave it to you. Oh, no, well, might as well. We can do it just to find out once and for all if I did it right. We add these up. There's 2 here. 13 and 1 is 14. Carry the 1. 6 and 3 are 9. And 1 is 10. Carry the 1. There's the 3,042. Like a miracle. Now, this is kind of difficult to visualize. You know, you say, gee, yeah, 100 times 10 is 1,000, but why is the noun 110 equal to 1,000? Well, again, I think we're going to go this way. Let me show you another way to do this that we call the area model, which is another very nice thing because it introduces geometry. Whenever you multiply 2 numbers, 2 positive numbers, you can always think of that as an area. In other words, let's say you were multiplying 234 by 13. If you had a rectangle that was 234 feet by 13 feet, to find the area, what would you do? You would multiply the 234 by the 13, and the label would be what? Feet, which is square feet. So let's just do that. Let's actually draw, I'm not drawing this to scale, but hopefully you'll get the flavor of this. Let's suppose that the length of the rectangle is let's say the unit is feet. It's 200 feet plus 30 feet plus 4 feet. And let's say that the width is 10 feet plus 3 feet. In other words, the 13 is broken down into one piece of size 10, another of size 3. The 234 is broken up into three pieces, 200, 30, and 4. And now, using the fact that the area of the rectangle is equal to the area of each of the constituent parts, what do we get? 200 times 10 is 2,000. 10 times 30 is 300. 10 times 4 is 40. 3 times 200 is 600. 3 times 30 is 90. 3 times 4 is 12. And lo and behold, the same six numbers that we have here are the same, I should say the six numbers that we have here are the same as the six numbers that we have here. The area model is a very nice way to visualize area, and it doesn't matter whether there's hundreds by tens or thousands by 10,000s, you can break it down the same way. And also what happens is, when you learn mechanically, I've seen kids do this. You want to multiply 201 by 103. Because it's okay, 3 times 1 is 3, 3 times 0 is 0, 3 times 2 is 6. 0 is nothing, so I'll skip it. 1 times 1 is 1, 1 times 0 is 0, 1 times 2 is 2. He says the answer is 2,613. Now, he should know immediately that this answer can't be right, because 200, if this was only 200 and this was only 100, the answer would already be 20,000. See, 200, the 2 times 1 is 2, and what do we do? We count the number of zeros. In other words, if 200 times 100 is already 20,000, how can 201 times 103, which is bigger, be only 2,613? The truth of the matter is that what that student did was, by putting the 1 over here, he may have called this 100, but by putting it here, where did he put it? In the tens place. What he really did, believe it or not, was he didn't multiply 201 by 103, he multiplied 201 by 13. See, 3, 0, 6, 1, 0, 2. This problem is the correct way of doing, is the incorrect way. How should I put it? I'm getting tongue twisted myself, but it's not a problem here. This method here, which was wrong, would have been the correct way to do this problem. Unfortunately, that wasn't the problem I'm trying to solve. Now, I watched my own children learn this, and they learned a very nice mechanical way. They said 3 times 1 is 3, 3 times 0 is 0, 3 times 2 is 6. Now I got to multiply by 0. 0 times 1 is 0, 0 times 0 is 0, 0 times 2 is 0. What did this do? You added absolutely nothing here, didn't it? This is a 0. But what it did was, by indenting, it made sure that the 1 came under the 1 in 100. You see what happened? In other words, if you did this by the distributive property, 201 times 103 is 201 times 100 plus 3. Well, 201 times 100 is 20,100, which, by the way, if I put the zeros in, that's what this comes out to be. 201 times 3 is 603. That's this number. And so by doing this, all you really did was do this the so-called rote method way, but by putting in the whole row of zeros, you made sure that the next row started in the appropriate place. Now, it's interesting, as you study math, you can also make it come a little bit more alive by putting in some historical stuff. The ancient Egyptians had a method called duplation. And in the method of duplation, all you had to know was how to double numbers and add. In other words, if I could multiply by 2 and add, I could do any multiplication problem. See, let's look at the numbers. Start with 1. I double it, I get 2. I double that, I get 4. I double 8, I get 4, I get 8. Double 8, I get 16, 32, etc. It turns out that any whole number can be written as the sum of powers of 2. For example, let's go back to the problem of 234 times 13. How can I rewrite 13 in terms of this? Well, I can't take out 16 from 13, but I can take out an 8. If I take out 8 from 13, there's still 5 left. From 5, I can take out a 4, and there's still 1 left. So I can write 13 as 8 plus 4 plus 1. So here's how the method of duplation worked. The Egyptians said, okay, 1 times 234 is 234. Now I'll just keep doubling. 2 times 234 is 468. Now I'll double this number, get 4 of these. That's 6, okay, 936. Then I'll double this number. That will give me 1872. So what does he get now? He has these powers of 2. 1, 2, 4, 8. Now which ones did he want to add up? He wanted the 8, the 4, and the 1. So he says, okay, I'll take this guy, and this guy. If I take 1 of these, and 4 more of these, and 8 more of these, that gives me 13 of these altogether. It's also what? 234 plus 936 plus 1,872, and he gets the same 3,042. Very nice historical situation. Also a great way for kids to drill and have fun at the same time. Multiply out the numbers the right way, meaning the traditional way, then multiply them out using duplation and see how that all works out. But I guess that's about enough for today. So let's come to our practice problem, where I ask you to pause the video, look at the question, answer it, and then come back and look at our solution. And what I want you to do here is, again, the power of the distributive property. Use the fact that 998 is 1,000 minus 2 to compute the product 234 times 998. Okay? And when you finish, come back and I'll show you my solution. See, 998 is 1,000 minus 2. So when I multiply 234 times 998, I'm really multiplying 234 by 1,000 and then subtracting 2 times 234. Now, in my head, it's pretty easy to see that 234 times 1,000 is 234,000. And it's also not too difficult to see that 2 times 234 is 468. So by subtracting 468 from 234,000, I get this answer. Okay? And that seems to be a lot easier than doing this. In other words, it gives me a very good estimate for the correct answer. And I know that the answer seems reasonable because the fact that 234 times 1,000 is 234,000, I expect the answer to be pretty close to 234,000. And if you want to make this into a word problem, suppose you buy 1,000 items at $234 each, but then you return 2 of the items. Well, if you bought 1,000 and you return 2, you've only bought 998. But by returning the 2, you also got $234 back twice. So you originally paid $234,000. You were given a refund of $468, and that led to a total amount of $233,532. Well, hopefully this is enough for today, but I also hope that it showed you why I really enjoy seeing multiplication explained in terms of the adjective-noun theme. It takes much of the mystery out of the subject, and we're going to show even more exciting things when we do unmultiplying next time, which is more commonly known as division. But until next time, have fun, work hard, and I'm looking forward to seeing you again. Bye-bye.